Hey class, here's a video for you all regarding problem 41 on the Wiley homework. What we have going on here is kind of a crazy problem. We got a person here in the circus that's going to be launched out of a human cannon of sorts, and he's going to go flying and land into a net some distance away. In addition to probably getting quite the thrill, he also has a lot of physics going on with him, so we're going to try to figure out some of that. So as we read the problem statement, there's a handful of pieces of information that are given to us. One piece of information we're given is the fact that the cannon is being fired at a given angle, somewhere probably around 50 degrees, depending on what your exact number is. We're also told that the rubber bands or the spring that's used to launch him is being pulled back some distance, that I'm going to just go ahead and give a value of x for the distance that he's going to be pulled back into his cannon or spring. And then we know also we're given the fact that he's being launched some other distance. Here I'm going to go ahead and maybe call this distance s from the cannon to the net. And we're told that the height above the ground that the net is at here is the same height, so here's our ground, is the same height that the top of the cannon is above the ground. So the question then that we're asked as this guy goes flying through the air here is what the spring coefficient is, the functioning spring coefficient that's required for him to be able to complete this launch as he goes up here and comes and lands in his net. So pretty wild and crazy problem, but also a very good one. So what you're going to hopefully be wanting to do to try to solve this problem is consider, at least in some portion, the concept of conservation of energy. But to get you started, I'm going to help you think about the problem and breaking the man's travel into three different locations. So location one is down here when he's just leaving the cannon, or excuse me, when he's just about to start his progression up the cannon, when he's fully pulled back in his spring or his slingshot. Position 2 right here as he leaves the cannon, and then position 3 is over here when he hits his net. So what we can do is, if we consider his transition from position 1 to position 2, we can use the concept of conservation of energy in order to try to evaluate what the spring constant that's needed for him to launch. So if we consider the idea of conservation of energy, we know that that tells us that kinetic energy initial, and instead of initial I'll just go ahead and use 1 since we're using points 1, 2, and 3 in here. So the kinetic energy at point 1 plus the potential energy he has at point 1 plus any work being done by non-conservative forces must be equal to the kinetic energy he has at point 2 plus the potential energy he has at point 2. So the question is, which of these types of energy does he have at each point? Well, at point 1 he has not yet begun moving, so that means that his initial kinetic energy should be 0. We also know that there's not any work being done by outside forces, since we're told we can ignore things like air resistance. So as a result, the only energy he has when he starts is potential energy, and that's the energy that's stored in his rubber bands or his spring, and so it's elastic potential energy. So it's going to be 1/2 k, the value we're trying to solve for, multiplied by x squared, where x is the distance that the rubber bands are pulled back. So we know that must be equal to his kinetic energy as he leaves the cannon, so that's going to be 1/2 his mass times his velocity at point 2 squared. And just so you understand and we're clear, I'm going to move this 2 since it's kind of in the way here. But just so you are clear and understand, the velocity that we're talking about is his velocity coming out of the cannon at a degree or an angle of theta here. So this here, this green velocity that I just drew, that's his velocity at point 2, at the angle of the cannon. So that's his velocity at that point, and then also, as we can observe here, he also moves up in height a distance h. and so we must also include his gravitational potential energy, so plus mg times h. So this k value here is what we're trying to solve for, but the question is, which of these other values do we have, which of them do we need? So k is what we want, x is given to us in the problem statement, mass is also given to us in the problem statement, but what we don't have is, what we do need to figure out though, which we don't know, is the velocity at point 2 and the height h. So let's see if we can figure those out. If we can, then we can use our conservation of energy equation right here to solve for the k value. So the value of h, as we can see in our picture here, if we consider this triangle that's made up by him in the cannon, the ground, and that height h, if you look at that as a triangle, maybe I'll draw it over here in blue, that same triangle, we know this side has a distance x, this is the h here, and this is the theta that we're given in the problem statement. So we can clearly see that h is just going to have a value equal to x, the hypotenuse, multiplied by the sine of the angle that we're given. So right there, you can plug that in for h. Boom, alright, that's good. And then the next thing you need to do is try to figure out the velocity at point 2. That is trickier to do. And in order to do that, we're going to have to consider what happens in his transition from point 2 to point 3. So looking at point 2 to point 3, all we're given about that transition is his horizontal distance that I've labeled here as s. So if we think back, oh wait, what's this? It looks like he's moving in projectile motion, he's starting and ending at the same height, so that's nice. So we can actually use either our equations of motion or our range equation to try to solve for that initial velocity v2 as he comes out of the cannon. So I'm going to go ahead and use one of our equations of motion. So if we recall back, we know that our final x position is equal to our initial x position plus the initial velocity in the x direction times time plus 1/2 our acceleration times time squared. So this is a good and easy equation to use because we know that our initial position we're going to define as 0, so that goes away, and we know that our acceleration in the x direction is also 0, so that goes away. And so all we're left with is that our x final position, which is that distance s given to us, is just going to be equal to our initial velocity in the x direction times time, which is also given, or our initial velocity in the x is just equal to our distance divided by our time, and we know that the initial velocity in the x is just going to be equal to that v2 multiplied by the cosine of the angle. So if we put these two together, set these two equations equal to one another, you can see that the v2 that you're trying to solve for will just be equal to s divided by t times the cosine of the angle. So once you have v2 here, you should be able to take it and combine it with the other parts of our energy equation that you saw up here, plug it in, and solve this beautiful equation for the spring constant that will help successfully launch this guy into his little net, landing safely and not falling short and hurting himself. Anyway, his safety is in your hands, and I hope you guys have a great evening.